Good morning. Welcome to e-learning. I am P. Saktivel, Assistant Professor, Department of EEE, Thandai Government Institute of Technology, Vellore. Today's topic, three-phase semiconductor. This three-phase semiconductor is also known as three-phase half-controlled converter because it uses half of the devices as controlled device and another half of the devices as uncontrolled devices. This three-phase semiconductor converts the given three-phase AC into DC. The semiconductor uses mixture of diodes and thyristor. It is a one-quadrant converter, that is, it operates in the first quadrant where VDC and IDC both are positive. For one input cycle of supply voltage for alpha less than 60, it works as 6 pulse converter because output has 6 load current pulses. For alpha greater than 60, it works as 3 pulse converter because the output has 3 load current pulses. So this semiconductor can work as 3 pulse converter, also 6 pulse converter. It is the unique advantage of the semiconductor. It is the circuit diagram of semiconductor. It uses 3 thyristors and 4 diodes. 3 thyristors and 4 diodes. The load is RLE type, and this E may be the battery in the load circuit or back EMF of DC motor. Numbering of SCRs and diodes. T1, T2, T3 are the positive group SCRs. This T1, T2, T3 are positive group SCRs. Output voltage across the load terminal is controlled by varying the firing angles of this SCRs T1, T2, T3 only, because this D1, D2, D3 are the negative group of diodes, and the diodes are uncontrolled devices. So the output voltage cannot be controlled by using this diodes. So SCRs controls the output voltage by controlling the firing angles, and the freewheeling diode is connected across the load, and the diodes just act as a return path for the current. Grouping of devices. Thyristor pairs T1, T2, T3 are positive group of devices and are fired at an interval of 120 degree amongst them. Similarly, diode pairs D1, D2, D3 are negative group of devices and are fired at an interval of 120 degree amongst them. Firing of devices. Each devices from both group conducts for 120 degree. That is, positive group device conducts for 120 degree. Similarly, negative group device also conducts for 120 degree. The conduction of thyristor depends on firing angle alpha. Conduction of diode independent of firing angle alpha. Positive group of thyristors fired at every 120 degree amongst them. So similarly, negative group of diodes fired at every 120 degree amongst them. Commutation of devices. Positive group thyristors commutated at every 120 degree amongst them. So similarly, negative group diodes commutated at every 120 degree amongst them. Starting of conduction. Very similar to the full converter, for phase voltages, if alpha equal to 0, then the first thyristor T1 starts its conduction at omega t equal to 30 degree, because at omega t equal to 30 only, the first waveform VA becomes greater than the second and third waveforms. But for line voltages, if alpha equal to 0, then the first thyristor T1 starts its conduction at omega t equal to 60, because at omega t equal to 60 only, the first waveform VAB is greater than the other waveforms. Working for line voltages. The line voltages are VAB, VAC, VBC, VBA, VCA and VCB. For alpha equal to 0, SCRs T1, T2 and T3 also behaves as diode. That is, T1 is turned on at omega t equal to 60 for alpha equal to 0. Then in the negative group, the last device D3 starts its conduction at omega t equal to 120. T2 at 180, D1 at 240, T3 at 300 and D2 at omega t equal to 360 degree. These are the conducting pairs of the devices for the phase sequence of ABC. D2, T1, T1, D3, next diode. Then T3 and T2, is the next thyristor. Then T2, D1 is the next diode, and D1, T3, T3, D2. Conduction table. So this shows the conduction table for the conducting pairs, and for D1, D2, the voltage waveform is VAB. T1, D3, the output voltage is VAC. See here, first we wrote the positive group of devices. So similarly, this T2 is the positive group of devices, and the voltages are VBC and VBA. This table shows the starting of the conduction for various values of alpha. For alpha equal to 0 degree, the first thyristor T1 starts its conduction at 60, D3 at 120, T2 at 180, D1 at 240, T3 at 300, and D2 at 360. This conduction of the diodes is independent of the firing angle. So for all the values of alpha, the conduction of the diode never changes. This D3 starts the conduction at 120 degree. So similarly, this D1 starts the conduction at 240, and D2 starts the conduction at 360 degree. Only the conduction of the thyristor depends on the firing angle. For firing angle of alpha equal to 60, the first thyristor starts the conduction after 120 degree, that is 60 degree delay plus this firing angle 60, totally 120, and it conducts for another 120 degree. This is the conduction interval for the devices T1, D3, T2, D1, T3 and D2. Each device conducts for 120 degree. This is the conduction table for alpha equal to 0. This is the conduction interval. The first table is the conduction interval. T1 conducts from 60 to 180, D3 from 120 to 240, T2 from 180 to 300, D1 from 240 to 360, T3 from 300 to 420, that is 0 to 60 also, 300 to 360, 360 can be considered as 0, so 0 to 60, and D2 from 360 to 480, that is from 0 to 120 degree. This PGT, positive group device, NGD, negative group device, it is the pair and output voltage. So for alpha equal to 0 degree, the first positive group thyristor T1 starts the conduction at 60 degree, and it continues its conduction for next 120 degree, that is from 60 degree to 180 degree, the first thyristor conducts, and from 180 to 300 for next 120 degree, the second thyristor T2 conducts, and for another 120 degree from 300 to 420, the third thyristor T3 conducts. After this T3, this T1 will conduct for 120 degree. So before T1, the conducting thyristor is T3. See here, before T1, the conducting thyristor is T3. After the T1, the negative group after the 60 degree of this T1, after the 60 degree conduction of the first thyristor, the negative group of device will be fired. That is at 120 degree, this D3 starts its conduction. So never the conduction of this diodes will depends on the firing angle. This conduction of the diodes will be fixed, that is D3 from 120 to 240, and D1 from 240 to 360, and D2 from 360 to 480. So after this D2, the conducting diode is D3. So before this D3, the conducting diode is D2 for 120 degree. Now this is the combination of the devices. T3 D2, D2 T1, T1 D3, D3 T2, T2 D1, D1 T3 for first 360 degree, and the output voltages are from the conduction table VCB, VAB, VAC, VBC, VBA and VCA. So totally for one complete input cycle, that is from 0 to 360 degree, there are 1, 2, 3, 4, 5, 6 output pulses. So this three-phase semiconductor is known as three-pulse converter. The table shows the conduction table for alpha equal to 30. For alpha equal to 30, also it has 6 output pulses. And it is the waveform for alpha equal to 30 degree. It is the conduction table for alpha equal to 60 degree. From this, we have only 3 pulses for one complete cycle. That is, from 0 to 360 degree, we have only 3 pulses. That is VCB, VAC and VBA. There is absence of VAB, VBC and VCA. So for alpha equal to 60 degree, the three-phase semiconductor has only 3 output pulses. So this semiconductor is also known as 3-pulse converter. This is the conduction table and output voltage waveform for alpha equal to 60 degree. See here, for 60 degree, this T3D2, the output voltage is VCB. So the output voltage is VCB. It starts at the middle and goes for highest value, then it reaches 0. See here, it goes for the peak value, then it reaches 0, VCB. Next one is VAC. Here, this VAC. It goes for the peak value at this point. See here, it reaches the peak value, then it reaches 0 in another 60 degree. So totally each pair conducts for 120 degree. First 30 degree it reaches to maximum, and next 90 degree it reaches the 0 value. After alpha greater than 60, conduction of same leg devices, that is T1 D1, T2 D2, T3 D3 starts. It leads to short circuit and damage of devices. To avoid the above, after alpha greater than 60, freewheeling diode gets forward bias and starts conducting. During freewheeling period, the output voltage is 0 because it makes a short circuit across the load. We know that the voltage across the short circuit is 0. But the conduction of the freewheeling diode is limited to 30 degree. After 30 degree conduction of freewheeling diode, no device will conduct. When no device will conduct, the output voltage is equal to the back EMF of the DC motor. This is the conduction table for alpha equal to 90 degree. See here, this is T2 D2, the same leg devices conducts. So the freewheeling diode gets forward bias and the output voltage is 0. And next 90 degree, the elements conducting are T3 D2. For next 90 degree, the output voltage is VCB. So during the freewheeling period, the output voltage will become 0. Similarly, from 0 to 360 degree, 3 times the freewheeling diode comes into conduction, and during this conduction of the freewheeling diode, the output voltage is 0. And it is the input voltage and conduction table and output voltage and load current waveform for alpha equal to 90 degree. And it is a conduction table for alpha equal to 120 degree. So here, this same leg devices T2 D2 conducts for 60 degree, T3 D3 conducts for 60 degree, T1 D1 conducts for 60 degree. But for first 30 degree, the freewheeling diode starts its conduction. After the first 30 degree, the conduction of the freewheeling diode is limited, and for next 30 degree, no device will conduct. When no device will conduct, the output voltage is E. When freewheeling diode conducts, the output voltage is 0. It is shown in the waveform, where freewheeling diode conducts, the output voltage is 0, where no device conducts, the output voltage is P. This is the waveform for alpha equal to 120 degree. This gives the average value and RMS value for semiconductor. Thank you.